Okay, this is a video on the history of numbers, and this is part 2, Ancient Egyptian and Greek Numbers. My name is Christopher Scott Vaughn. I'm a math instructor at Montgomery County Community College. Okay, here we'll look at the ancient Egyptian numerals that date back to 3000 BC. That's about 5,000 years ago. Beginning of civilization. You can see this is really ancient Egyptian hieroglyphics that we'll be reading here. A symbol for 1 is a stroke, the symbol for 10 is an arch, 100 is a rope, 1,000 is a flower, 10,000 is this finger. Now if you look on YouTube or the internet, you'll find other ways in which that finger is actually more fully drawn. The image I have here is a real simple little broken line there, but it's also drawn as a more detailed finger. This 100,000 is supposed to be a tadpole, and you can see that drawn different ways also. And then finally at a 1 million, we have a symbol for 1 million in the ancient Egyptian hieroglyphics, which is this astonished man, which I think is appropriate. If anything is that big, you're kind of astonished, right? Imagine if I had $1 million, I would be in that kind of position, for sure. Okay, so I'm going to go through some examples. How about the number 421? So 421, again, they don't have anything like our modern positional number system. We have symbols for 100, and we need 4 of them to make 400, 2 tens, and a 1. And you know how it wouldn't really matter whether I put the 1 first, and then the 2 tens, and then the 4 100s. I could put it really in any order, and it would still be 421, as long as it was clear that it was all grouped together. So that's 421. Here's 503. That's 500 from the 5 symbols for 100, right? 5 100s and 3 1s. And I don't have a 0 in the ancient Egyptian number system. And the position doesn't really have that much significance. We could put the 1s first as an example, which we'll see later in some other examples. Here's 5003. Just look at the difference between 503 and 5003, and you can see how important that 0 is in our number system. That 0 indicates that now the 5 is in the 1,000 place in the modern Hindu Arabic. But here we have 5 symbols for the 1,000. 1,000 is this flower. I know mine are starting to look like alien women, but those are supposed to be flowers, and 3 1s. And then how about 10,204? So there's the finger, 10,000, and then 2 symbols for 100, and then 4 symbols for 1. Okay, how about try writing this in modern numbers? If you see, this is a chance to read ancient Egyptian hieroglyphics. If you could read this, that's a pretty fun thing to be able to do. So pause the video, figure it out, and then check the answer. Okay, so here's what I have. It's 1,200,000 and 3,000 all together is one number, so that's 1,203,000. It's kind of neat to think about how our addition uses the positions of those numbers, how convenient that is, and how really different that would have been if you were adding an ancient Egyptian. You could just group all the tadpoles together, you could group all the flowers together, and how many astonished men you have, and do your summation that way. I'm going to talk about ancient Egyptian multiplication, which is also very different than what we do, and I think it's going to be a neat thing to learn how that works. I think I have another example. Yeah, let's go now to the ancient Egyptian multiplication. Now, the reason that I want to do this is something that I hope that you would get out of this course, is that you begin to understand modern things in another point of view. I want to just for a moment go back and talk about how it was understanding the ancient Babylonian number system that enriches your understanding of how we tell time. And when you look at a clock now, you can think about the fact that if you are watching the time click from 59 minutes to another hour, now you know why that is. It's an ancient way of measuring a fraction. These are sort of the way in which we tell time, sort of developed into its form now, kind of in the Middle Ages, where it was before decimal numbers. Decimal numbers started in around the 1500s. So in the Middle Ages, people started thinking more carefully about breaking up a day into hours and breaking up those hours into minutes, and they were using Latin, and they were using an ancient method of fractions, which was the ancient Babylonian number system. So we have maybe you can start to have a better understanding of how we tell time and how it works because of learning the ancient Babylonian numbers. It's sort of a more enriching understanding of why we count 59 minutes, 60 minutes to make 1 hour and 60 seconds to make 1 minute. And then now here, as we begin to understand the ancient Egyptian number system, I'll talk about the multiplication, the way that the ancient Egyptians did it. And I think it's really interesting because it starts to enrich a little bit of the understanding of how modern calculators and computers do multiplication. They use a binary system, and that binary system ultimately you could say is essentially the same as the way the ancient Egyptians were doing it. So I think that understanding how the ancient Egyptians multiplied will enrich your understanding of modern multiplication on a computer and on a calculator. How does it even work? It's done the way the ancient Egyptians did it, at least in some respects. Okay, if you're going to multiply 24 times 16, the way that ancient Egyptians multiplied, it's really simple. It's kind of neat. It's fun to think about how this works. I'm going to make 2 columns underneath the numbers that I want to multiply. And the first column, I'll start with a 1, and I'll just keep doubling. 2, 4, 8, 16. You continue to write these numbers until you reach when you recognize that the next number will be bigger than what you started with, right? So the next number, if I continue doubling, that's 32, and that's bigger than what I started with. And I stop here, and what I do is I check off all the numbers that together would add up to 24. Now that will always work, and that's because what I'm really doing is kind of writing 24 in a binary system. And so you can write any number in a binary system. So if you were writing this in binary, we'd have a 0, 0, 0, 1, 1. And that's binary for 24. And then, okay, so that's the first column. And then the second column, you just copy exactly the number that you had. Like here, I'm copying the 16. And then you just double that. Continue doubling whatever you started with. So 16 and 32 and 64 and 128. These are just continuing to double. So it doesn't matter what you stopped here. You're copying whatever number this is. This is just 16. If this had been a 50, I would write 50 first, and then I would write 100, etc. I would keep doubling. So 16, 32, 64, 128, 256, those are all doublings of the original number. And then the neat trick is that you can just find whatever number you had checked off to add up to 24. Those are the numbers that you circle here, directly across. And it's those numbers that you add together. So it's just checking off certain numbers that add up to 24, and then add the corresponding numbers in this column together, and that's what you get. That's the answer. 384 is the result of 24 times 16. Okay, I have another example. Let's try this again. So try 23 times 15, and try this by the ancient Egyptian method, and then use your calculator to get the answer. And you're going to check it from the calculator and realize that your calculator is using binary, which is in a way, and the way that the calculator is actually doing it is ultimately very, very similar and to how the ancient Egyptians did it. You better understand how the calculator works if you know the Egyptian method. Okay, 23 times 15. So I'll start always in the first column with a 1, and then double, and continue doubling. I stop again at 16 because the next one's 32, and that would be larger than the 23. In the second column, I copy whatever is directly above. I copy that and continue doubling. So 15, double it's 30, double that's 60, double that's 120, double that's 240. Now what you have to do is go through and come up with checking off the numbers that add up to 23. Right? So 3 plus 4, that's 7, plus 16. That makes 23. That's the only combination that will add up to 23 out of those numbers. You could say in binary. If you were writing 23 in binary, it would be a 1, 1, 1, 0, 1 in binary. And then it's these numbers that are directly across that you're going to circle. And when you add the numbers that are circled, you get the answer. That's 345. So that's the ancient Egyptian multiplication method. Okay, now this is some ancient Egyptian hieroglyphics. Let's see if you can actually go in there and read this. Well, the only thing that you could really read, I suppose, at this point would be the numbers, and you've kind of gotten some hint here as to what they are. This is 7 single stroke symbols, so that's the number 7. Now what is this? This is 9 ones and 4 tens. This is really 49. The person who is translating this put the 9 first and then the 4, so don't make the mistake, it's not 94. It's not a positional number system. It didn't really matter what the position was. The 9 comes first and then the 4 tens come after, and it's still 49. So this is really 49, and so what is this? This is 3 ones, 4 tens, and 3 100s. This is 343. It's curious that it's the same whether you switch it or not in our modern number system. So this is a 1, 300, and 2 thousands. This is 2,301. And there's the finger. That's 10,000. That's 6 flowers. That's 6,000. That's 8 100. That's 800. That's 7. That's 10,600. 10,000. Oh, I'm sorry. 16,000 if you put it all together. 10,000 and 6,000. That's 16,807. This is now 10,000 plus 9 flowers. And the 9 flowers are 9,000. There's 607. Over here we have 2,801, 5,000. There's the 602. This is 11,204, 1,000 and 9,000, 19,607. So, and then the other symbols, some of these other symbols here are something I'm going to get to in a minute. They're talking about some inventory, and this leads to a ancient Egyptian word problem. And they're doing the multiplication over here on the far right column. This is a 1, this is a 2, this is a 4, and 4 and 2 and 1 make up 7. So this is really a multiplication problem in the ancient Egyptian method over here, and this is just a summation on this column. I have a translation that I'll show you. Here I've got the translation. It's switched the columns, but in one column you have a multiplication being done by the ancient Egyptian method. Think about how would you do 7 times 2,801. 7 times 2,801 in the ancient Egyptian number system, it'd be easier to take a smaller number and start with 1 on that one, and then a double, and then a doubling, and already I've got 7 right there. And then just copying the 2801, doubling it. 2801 plus 2801 is 5602. And then 5602 plus 5602 is 11,204. And then it's just those 3 numbers that get added together, that makes 19,607. And this is a different calculation over here. These are powers of 7 being added together. 7 plus 49 plus 343 plus 2401 plus 16,807 adds up to 19,607. And it's the same result if you multiply or if you add this column. And it was that papyrus that you were looking at. Papyrus is an ancient Egyptian paper. It was doing the same, it was getting the same total in either calculation. And there's some speculation that what that ancient Egyptian document is actually illustrating is essentially a word problem in an ancient math word problem. And so a translation of some of these other hieroglyphic symbols has produced this word problem. An ancient Egyptian version, it says, there are 7 houses. In each house there are 7 cats. Each cat catches 7 mice. Each mouse would have eaten 7 ears of corn. If sown, each ear of corn would have produced 7 hecad of grain. How many things are mentioned together? And with that question, you get that answer that's on the Egyptian papyrus, and it's done 2 different ways on that papyrus. There's a book that we will study some later in this course from Fibonacci in the 1200s, where he creates a word problem in his book in Latin that is very similar to that ancient Egyptian word problem. And the version in the Middle Ages was written this way: 7 old women went to Rome. Each woman had 7 mules. Each mule had 7 sacks. Each sack contained 7 loaves. And with each loaf were 7 knives. And each knife was put in 7 sheaths. And then there is a nursery rhyme that you might be familiar with that we could say is now a modern version, although it's about 200 years old. This is from the 1800s. And the nursery rhyme says, as I was going to St. Ives, I met a man with 7 wives. Each wife had 7 sacks. Each sack had 7 cats. Each cat had 7 kits. Kits, cats, sacks, wives. How many were going to St. Ives? So imagine how this is so similar to the Fibonacci version, which was similar to the ancient Egyptian version, and it's fun to think about that this is a word problem that's maybe close to 5,000 years old. So can you figure out, let's try this modern version. Can you figure out the answer to that? As I was going to St. Ives, I met a man with 7 wives. Every wife had 7 sacks. Every sack had 7 cats. Every cat had 7 kits. Kits, cats, sacks, wives. How many were going to St. Ives? There's a trick here where you might say that the only person going to St. Ives was the narrator, the person that refers to himself as I, or herself as I. So perhaps the answer is only one. This I meets a man with 7 wives, but it doesn't say that the man and the 7 wives are going to St. Ives. So you could say as a trick answer, yeah, there's only one person going to St. Ives. Well, that's a great answer. Let's take this a little bit further and say how many, assuming everybody and everything that's mentioned is all going to St. Ives. And if that were the case, we need to look at powers of 7 and add them up. We'll say there was the narrator, there was the man, there were 7 wives. Each one of those 7 wives has 7 sacks, so that's 7 times 7 is 7 squared, 49 sacks. Every one of those sacks had 7 cats, so that would be 49 times 7, it's 7 to the third, it's 343 cats. And then every one of those cats has 7 kittens, so it's the 343 times 7, that's 7 to the fourth, 2,401 kittens. If you add all that together, 2,802. Okay. And next I'm going to look at ancient Greek numerals. The ancient Greeks, back in 1000 BC, were using letters that they used for their alphabet also for numbers, which must have been awfully confusing. So here's a translation from what we now use, the numbers that we now use in the ancient Greeks, and you see how it's really different. They had a symbol for 10, they had a symbol for 20, and a symbol for 30, and once they hit 1,000, they had a little, they would use a comma, that would, something that's similar to a comma that you could do a 1 with a comma, and that was 1,000. So here's some the names of these symbols if you want to figure out how to pronounce them. So let's take an example. How about 345? Well, this is really pretty simple. If you've got the table, I need a symbol for 300, I need a symbol for 40, and I need a symbol for 5. You just put those together, and answer looks like that. Tau, mu, epsilon. It's 345 in the ancient Greek number system. How about 949? How would you write that? I need a symbol for 900, a symbol for 40, and a symbol for 9. And those are all different symbols, so it's really complicated to remember all of that. Imagine, have to look this up every time you want to write a number. It's just, no wonder we don't use this anymore. Right? This is a very difficult to work with. And here's 888. How would you write that? Well, if you've got the table, it's very easy. A symbol for 800, a symbol for 8, and a symbol for 8. This is omega pi, and I think this is eta. 503. So compare 503 with 53, and I have a symbol for 500, phi, and this is gamma, phi gamma. That's 503, and then if I want to do 53, this looks like a V. This is a new gamma, and there was no symbol for 0 in the ancient Greek number system. So, okay, well, so this is where I'll end with this video.